Present the conference. Divide and Conquer and Systems Partition and Decomposition. Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Imagination is the highest form of research. Albert Einstein. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers, will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. However, for a long time, mathematics oriented to parallel optimization has been undervalued. In many of the academic programs they are totally ignored, and many of the students do not feel the need to use them. This lecture is an overview of what parallelism and optimization entails. Mathematical revolutions, from arithmetic to parallel thinking. A brief history of mathematics, focusing on the evolution of optimization applied to real-world problems. The origin of mathematics is the arithmetic, which begins its development with the appearance of humanity. The appearance of algebra is in the near to the year 800 BC. Many centuries passed since the apparition of arithmetic. Muhammad ibn Musa al-Khwarizmi, mathematician and Arab astronomer, introduced European mathematicians into the Indo-Arabic numerals and in the fundamental principles of algebra. The evolution of algebra starts from a school notation, oriented to small models, not scalable, to become a professional, industrial, and scalable algebra, oriented to the present modeling of the large systems that make up the real world. If two algebraic formulas are joined, a new algebraic equation is obtained that retains the same structural characteristics of the original equations. This transitivity law may be extended to mathematical programming models, MP, which in essence is a collection of algebraic elements. Additionally, the entire mathematical representation of a controlled real-life system is represented by one and only one reduced-form math model, using algebraic equations to describe the system and its dynamic. It can be said that there is only a reduced way to write an algebraic equation. This is independent of the symbols that are used to represent the physical or logical relations. Then it is possible to join two MP problems to obtain a new MP problem. It is also possible to divide an MP problem into two MP problems. The principles of transitivity between MP models can be extended to more complex structures, such as those derived from the partitioning and decomposition of systems, to apply large-scale optimization methodologies. In this way, the new vision of mathematical programming involves defining the relationships between problems, as the next step after the definition of the equations that compose them. The difference that mastery of algebra creates with respect to arithmetic is an abyss, is not a gap. Perhaps the second great mathematical revolution, it is the birth of the fundamental principles of optimization. Based on differential calculus. René Descartes was a French mathematician, physicist and philosopher, considered the father of the algebraic and differential geometry. Sir Isaac Newton was an English mathematician, physicist, astronomer, and theologian, widely recognized as one of the greatest and most influential scientists of all time. He was a key figure in the philosophical revolution known as the Enlightenment. Newton made seminal contributions to optics, and shares credit with German mathematician Gottfried Wilhelm Leibniz for developing infinitesimal calculus. Joseph Louis Lagrange was an Italian mathematician and astronomer, later naturalized French. In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. Using the implicit function theorem, the seminal Lagrange idea is to convert a constrained problem into a form such that the theory of an unconstrained problem can still be applied. George Bernard Dantzig was an American mathematical scientist who made contributions to industrial engineering, operations research, computer science, economics, and statistics. Dantzig is known for his development of the simplex algorithm for solving linear programming problems, and for his other work with linear programming. In statistics, Dantzig solved two open problems in statistical theory. The primal simplex algorithm can be considered the starting point of applied mathematical programming, and the birth of computer-oriented mathematics. Mathematical programming is characterized by having an objective function as decision criteria, and a mathematical model, based on a set of constraints that represent the industrial's process, and the business rules. Since its birth, computer-oriented mathematics has evolved in speed, and in the ability to solve increasingly complex problems. The image presents the evolution of the Gurobi solver, from its first version, in 2009, to the last in 2023, this for discrete optimization problems. The difference that the mastery of computer algorithms creates with respect to the solution of problems by humans, is an abyss, is not a gap. In a relatively short time, 25 years, mathematics oriented to parallel computing emerges. This new revolution is not pressured by parallel processing, since it did not exist. The pressure is generated by the need to speed up the solution of large problems in a digital computer. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. Benders partition, or Benders decomposition, is a technique in mathematical programming that allows the solution of very large mixed linear programming problems that have a special block structure. This block structure often occurs in all real applications. The importance of Benders' theory, which followed the work of Dantzig-Wolff, is that it resulted in parallel optimization, based on the theory of duality. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex, which today is the key to a dynamic language for cognitive robots, based mathematical programming algorithms to build artificial hypothalamuses. Duality theory is the key to create a generalized language between robots, or algorithms, that represent different types of systems. Today, it is the support of parallel and distributed artificial intelligence, that is the base of artificial brains. The growth of parallel optimization-oriented technologies has been significant over the past 2 decades. The image presents the growth of Benders' theory from its inception in 1962 to 2016. The green bars, based on a visual projection, presents the expected growth in these years, which is exponential. The power of Benders' theory. Since its formulation in 1962, it has proven to be an effective methodology to solve complex problems that cannot be solved using only best basic optimization algorithms, Plex, Gurobi, Express. Algorithms based in Benders' theory can solve NP-hard problems in reasonable time. It has proven to be an effective methodology to solve complex problems that cannot be solved using best mathematical solvers. Benders' theory is a mature methodology that are in the accelerated growing phase. There are many possibilities to research in Benders' theory. There are a gap between the research in mathematical programming and the application of the large-scale methodologies in real-world solutions. Benders is a primal methodology, work in the feasible zone. It is an advantage when the time is a limitation in the optimization process and in real-time distributed optimization. The parallel large-scale optimization technologies are the actual state-of-the-art of optimization. Benders facilitates the understanding of complex systems, dividing the problem in subproblems that represents the operation and each component. It is necessary in the real-time distributed optimization. Not a way, the advanced optimization modelers must begin its work using large-scale methodologies, because they need to solve large-scale problems that the final users need, real world. On the other hand, the speed increase provided by large-scale theories is significant. The table provides information on various types of problems, solved with several variations of Benders' theory. The column time ratio solver/Benders presents the relationship of solution times for different sizes of problems. The content is Benders times faster. In 1983, Tony Van Roy created the cross-decomposition approach to solving large-scale optimization problems, based on partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Bender's theory. Cross-decomposition, CD, is applied when the coordinator subproblem partition has been performed, and a new partition or decomposition is desired to be performed on the coordinator using a basic theory different from the one previously used. CD is the harmonic coordination of communications between the different subproblems wherein each of them information is processed according to the theory used, BT or RL, and information is exchanged according to the connectivity of the hierarchical scheme of the subproblems. Cross-decomposition makes it possible to establish complex optimization processes, in which multiple large-scale methodologies are used, which allows to adjust the problems to the most convenient methodology for the solution of each subproblem. From the point of view of multi-layer structures, cross-decomposition gives rise to the exchange of information between multiple layers, of different columns, such as the real structure of the human neocortex. Again, the difference that the domain of large-scale optimization creates with respect to sequential optimization is a chasm, not a gap. Given the complexity of the real world, which involves mathematical models of all types, linear, nonlinear, discrete, continuous, convex, non-convex, etc., it cannot be thought that with a single methodology, all the problems that make up an artificial brain can be solved. Therefore, it is required to have access to multiple large-scale optimization methodologies, which, using the principles of cross-decomposition, connect all mathematical problems, to perform autonomous distributed optimization in real time. Divide and conquer is a strategy that involves breaking down a complex problem into smaller, easier to solve subproblems, and then combining the solutions of these subproblems to get the solution to the original problem. This strategy is applied both in the resolution of computational problems and in political and military strategy. Divide, split the original problem into multiple subproblems until the smallest subproblem is reached. Conquer, from the smallest subproblem, the solution to the original problem is built, merging from the bottom up, the solutions of the subproblems. Considering the complexity, for the initiation of a combinatorial problem, High has frequently used the divide and conquer strategy. A problem that must be faced is the feasibility of hard restrictions, in which case the source of the infeasibility must be identified and corrected. Two sources of infeasibility must be considered: mathematical model with errors in its formulation, and errors in model data. High's experience taught that trying to prove the unfeasibility of a monolithic problem can take an unreasonable amount of time. Therefore, a version of the model was built that would allow the feasibility analysis to be carried out efficiently and quickly. To conquer, the model is divided into subproblems that can be solved, sequentially or in parallel. In the final stage, the subproblems are merged to obtain the feasible or unfeasible solution. This process will always be faster and use less memory, possibly solving non-solvable problems in a monolithic way. Problems are the result of the modeler's experience. The optimization process is organized sequentially in such a way as to facilitate and accelerate the obtaining of a feasible initial solution. The idea is to carry out the optimization process in n steps, in which the first n1 are related to the check for infeasibilities and the last with optimality. High has proven, in the real world, the effectiveness of this method. Soft constraints, penalized for their violation, can hide hard feasibility issues, since, depending on the cost of the penalizations, it is impossible to differentiate a feasibility error from the activation of the artificial variables related to the violation of soft restrictions. Splitting the process into three phases avoids this problem. Case: the search for feasibility. The standard process is to solve the original monolithic model, using an optimization algorithm appropriate to the format of the problem. This focuses on the use of algorithms from commercial houses, such as IBM Plex, Gurobi, Express, that have tools to identify the ISAs group. Based on its experience, High has developed its own methodologies for IS management. The first method is based on the classic two-phase optimization. To do this, the phase 1 model must be generated, which involves relaxing all or part of the restrictions. In the case of constraints, This involves including a relaxation error for each constraint and substituting the objective function for a sum of errors, which can be linear or quadratic. If the optimal solution is equal to 0, the problem has a feasible solution. In case of feasibility, in the second phase optimality is sought and the problem is solved. The process implemented by HI divides the stage of achieving hard feasibility into multiple optimization subproblems, whose solution must be feasible to guarantee the feasibility of the monolithic problem. The subproblems, being independent, can be solved in parallel. Top-down and bottom-up are contrasting approaches to problem-solving, decision-making, and mathematical analysis that are applied in many fields. The top-down method starts with a broad overview and progressively breaks it down into smaller details, while the bottom-up method starts with specific details and works upwards towards a larger, more complete picture. Choosing between a top-down and bottom-up approach depends on the specific goals, complexity of the project, and the culture of the organization. Many researchers believe that a hybrid approach that combines the strengths of both methods may be the most effective. HI believes that, if possible, the bottom-up approach is most appropriate. The top-down approach to establishing the functioning of the aggregate system is based on data that approximate mathematical modeling using empirical rules of disaggregation, while the bottom-up approach, to provide information and refine the details of system modeling, relies on mathematical modeling of the atoms in the system that are simply aggregated by means of mathematical rules. The term bottom-up describes a process that starts with the individual components or most basic level of a system and works its way up to the complete or highest level outcome. These components correspond to the atoms of the system. It is normal to know how each atom works, but there are not always mathematical rules that describe the system, and therefore it must be constructed as the sum of atoms, with all the interactions that this implies. In computing, the bottom-up approach is heavier than the top-down method, but the evolution of computer science has solved this problem. Therefore, in this case the gain of dividing the problem is in the knowledge and the quality of the modeling that can be done. Pandemics, regional planning, disaster management and homeland security. Below is a comparison of traditional pandemic models, based on a top-down scheme, with a modern bottom-up model, implemented because of the COVID-19 pandemic. The results that serve planners should be divided by suburbs of the city. The top-down model takes the city, or the region in with a single system of differential equations tries to explain the behavior of the pandemic in the region, using socio-demographic factors based on aggregate data, such as population, age, economic level and other factors. The bottom-up model divides the city into atoms, suburbs of the city, and constructs the functioning of each of them considering the actual data existing in the region's information system. The following is the theory of two complementary models developed following this approach. The document, CIMER-RS. General Model of Simulation of Epidemics, Multi-Infected States, Multi-Socio-Demographic Segments, Multi-Region Mobility. Theory, corresponds to the model of differential equations for the simulation of pandemic processes. The document, CIMER-RS-OPT. Epidemic Management Optimization Model, Control Policies, Vital Health Resources, and Vaccination. Theory, corresponds to the optimization model, which integrate the differential equations model, for the optimal management of pandemic processes. Aggregate modeling is the traditional one. This implies a model of low mathematical complexity. The next step, since a better visualization of the spatial distribution of the pandemic is required, is to perform a disaggregation for each of the atoms, that are the basic areas. The disaggregation is empiric, because it is based on subjective rules, which do not reflect what is really happening in the territory. The detailed or bottom-up modeling is a high mathematical complexity tool. It is based on the detailed modeling of each of the atoms and their interrelationships. From the atoms, and considering all the interrelationships, the pandemic is simulated in such a way that it reproduces the behavior of the pandemic in each atom. The next step is the scientific aggregation of results, to explain the behavior of the entire system. This procedure is totally objective, and produces a realistic evolution of the pandemic. The modeling implies that the CIMER-RS model receives as input the detailed description of the city, and produces as a result, the detailed simulation for each area in which the space has been divided. The mathematical complexity that must be handled is reflected in the number of differential equations that must be solved. In the case of Bogotá, if the city is divided into neighborhoods, equations would be 738,048, and it requires high-performance computing resources to solve the problem. This contrasts with the three equations of the SIR model for the whole city. Partition and decomposition is the process of breaking down a large, complex system into smaller, more manageable parts. An approach to solving large stochastic dynamic problems using multilevel Bender's theory and Lagrange relaxation. The procedure aims to establish problem families in such a way that they generate multiple cutting planes when a single family problem is solved. Families are related to zones, sectors, time, types of decisions, projects, and/or random conditions. For high, the following definitions are used. Partition, the action of dividing a problem into two sub-problems by establishing a hierarchical relationship between them. Decomposition, the action of dividing a problem into multiple sub-problems with the same hierarchical level. Partitioning and decomposition systems for optimization problems, TOP, is a mature field in operations research, which is a suitable strategy for the TOP problem. Two basic alternative strategies are usually used. Lagrange relaxation or decomposition, LR, also known as Dantzig-Wolff decomposition, DWD, and the partition and decomposition of Bender's, or Bender's theory, BT. The general idea is to relax the global restrictions that cover large part of a problem. The basic mechanism is to divide the original problem into smaller subproblems that are coordinated by a master problem. An iterative procedure is then used to achieve convergence towards an overall solution. There are two aspects to consider when choosing which constraints to place on the subproblem. It should be easy to solve, as it is re-optimized several times, and it should provide good quality limits in the intermediate solutions. TOP should have a decentralized topology, which is a suitable structure for some partitioning and decomposition strategies. Uniting the theory of generalized decomposition and partitioning, it is possible to structure complex systems. Consider a case where investments and operations must be coordinated in a system that has multiple levels of partition and decomposition. Initially, an integrated model that involves investments and operations are considered. The first step is to consider a partition of the integrated model into two models, an investment coordinator and an integrated operations model. Now, taking into account the system as the integration of multiple sectors, it is possible to divide the operation model into two levels. The second one can be decomposed as the union of multiple operation models, one for each sector. If the sectors integrated by zones are considered, a new partition and decomposition process can be accomplished. If time is considered, a new hierarchic level can be generated. We would obtain a dynamic coordinator for each zone or sector, and a static operation model for each period of the planning horizon. A similar process can be followed for stochastic optimization models. As a starting point, IT considers an integrated model that gathers multiple models under synthetical random conditions for the industrial operations. The first step is the decomposition of the stochastic model integrated in multiple models. The first step is the decomposition of the stochastic model integrated in multiple models. Systems are characterized either by the families of problems they include and by the coordination of information that flows between them. Making a parallel with neural nets, the concept of problem family can be assimilated to a neuron class, and the optimization process can be defined as a complex communication system between neurons. In the synchronous schema, each cycle ends when all the problems have finished processing the data. In the asynchronous parallel scheme, information is disseminated, and each neuron processes the information as soon as possible, and generates new information. The diagram presents the structure of a simple artificial neuron. Hai has created the concept of the smart artificial neuron, which is associated with a mathematical problem that the smart neuron must solve. The intelligent neuron is linked to an entity or object of the industrial system. An intelligent neuron can be made up of other intelligent neurons, since each of them represents a part of the system associated with an optimization problem, which is integrated with the others. This facilitates a unified paradigm for mathematical programming and neural network-based artificial intelligence. Real case, Troll West Oil Rim Operation Optimization. Case based on the paper. Real-time production optimization in upstream petroleum production, applied to the Troll West Oil Rim. An offshore oil and gas producing group has many internal couplings, such as mass and pressure balances, and well routing. In addition, there are only a few common limitations, in this case the total production of gas and water. By relaxing these constraints, a decomposition strategy can result in a subproblem for each cluster I. Each subproblem can be assigned its own part of the objective function, based on a cluster, and a second mandate that considers common capacity constraints. The problem has a decentralized topology suitable for decomposition strategies. An oil and gas producing group has many internal couplings, such as mass and pressure balances, and well routing. In addition, there are only a few common limitations, in this case the total production of gas and water. By relaxing these constraints, a decomposition strategy results in a subproblem for each cluster. In Lagrange relaxation, LR, the basic idea is to attach Lagrange multipliers to the common constraints in the model and relax them in the objective function, whereas Dantzig-Wolff decomposition, DWD, handles the common constraints on a master problem. The structure of the two approaches is the same. The master problem includes the total flow variables, pressures, and local flows are part of the cluster subproblem. Decomposition involves a problem for each cluster that can be solved sequentially or in parallel. In their original form, subproblems correspond to MIMP problems that are converted to MILP by linearization of nonlinear functions. When applying DWD, or LR, the subproblems are the same. However, Lagrange multipliers can be updated in three different ways. DWD includes as new variables, column generation, the weights of the convex functions for the extreme points, and LR can be based on one of two methods, supergradients or cutting planes. Foss et al. Use LR based on supergradients, which can be interpreted as a math heuristic method. Gunnerud and his research group at the Norwegian University of Science and Technology present a model of the Troll West Oil Basin, an offshore oil field on the continental shelf west of Norway, with severe production optimization problems due to velocity-dependent gas cone wells and that the oil phase lies between the water and gas phases. The Troll West Oil Rim has multiple independent reservoirs from which multiple wells feed multiple manifolds connected by pipes. The varieties belong to clusters. Pipeline flows provide input to processing facilities where fluids are conditioned for export. This is commonly referred to as the real-time production optimization, RTPO, problem that is used in the upstream industry today. RTPO is associated with systems with a decentralized structure, which means that common restrictions are quite few. Typically, RTPO is treated in a quasi-dynamic manner by reoptimizing a stationary optimization problem, usually once a day. The diagram presents the offshore field, which is composed of 8 clusters, each of which can operate independently of the others. However, the planning of the field must be integrated. This is due to the joining of all clusters through the production line. While production functions are modeled by linearizing a nonlinear model using a linear function by parts, this converts an NLP problem into a MILP problem. To minimize error due to piecewise linearization, good accuracy and small intervals between interpolation coordinates are needed. This results in many variables and will therefore be computationally expensive. To handle this, it is possible to dynamically insert interpolation coordinates in areas close to the solution. Initially, the problem is solved only by containing a small set of interpolation coordinates. The solution is then located, and more interpolation coordinates are inserted into that area and optimized again. When acceptable accuracy is achieved, the problem converges, with the added advantage that error limits can be calculated in the solution of the optimization problem. Gunnerud and his team start by assuming linear constraints and continuous variables, i.e., an LP problem rather than a MIL problem. Then the master problem is a reformulation of the integrated problem, CRICPO. Each feasible base point for each cluster is represented as a variable in the master problem and represents a production configuration specific to this cluster. The number of feasible basis points for any practical problem can be clearly prohibitive, and only a small number of these feasible basis points will be basic in the master problem. Then the idea is to constrain CRTPO by reducing the number of feasible basis points. DWD starts with some feasible basic points and checks whether the solution of the built-in problem is within a convex combination of these points. If this is not the case, new feasible basic points are included in a structured manner until the optimal solution has been found. When applying DWD to the RTPO problem, the subproblems will be identical to LR if the same common constraints are subject to relaxation. However, while Lagrange multipliers are updated using a subgradient heuristic in the case of LR, the update in DWD is done by solving a master problem of LP. Dantzig-Wolff decomposition algorithm. Choose two feasible initial base points for each optimization problem in a cluster. One of these points can be obtained by assuming dual variables for global constraints equal to 0, the other point can be obtained by assuming another value for the dual variables close to 0. Since the important thing is to obtain two feasible points for each of the subproblems of the cluster, which may be close to the optimal solution. Specify the master problem for the given set of feasible basis points, then solve it and calculate the values of the Lagrange multipliers for the global constraints. Solve optimization problems for each cluster using the Lagrange multipliers obtained in step 2 as the objective function. If the solutions to all the local optimization problems have not changed, the optimal solution has been found, and the algorithm ends. For any problem, the solution of which lies outside the convex set defined by the feasible basic points used in 2, add the actionable basic points to the master problem and go to 2. Therefore, RTPO is resolved, including also these new feasible base points generated in 3. 4 experiments were performed for each methodology. The difference between the cases is the difference in the number of clusters, 2, C2, 4, C4, 6, C6, and 8, C8, in Troll C. The gas capacity for each case increases with the number of groups. The fact is that the decomposition strategies, DWD and LR, are faster in all cases than the global method, full space, F, S, except in the smallest case, C2. F, S, does not converge to its termination criteria after 12 hours for the case of 8 clusters and typically has difficulty resolving issues that consist of 6 clusters or more. F, S, stopped after 12 hours, with just over 7.5% in the duality gap. DWD and LR end all problems with a duality gap of less than 0.5%. DWD shows superior performance to LR in terms of efficiency and robustness. However, LR's performance is superior to F, S, S, demonstrating that as problems grow in complexity, so does the advantage in favor of large-scale methodologies. 4 experiments were performed for each methodology. The difference between the cases is the difference in the number of clusters, 2, C2, 4, C4, 6, C6, and 8, C8, in Troll C. The gas capacity for each case increases with the number of groups. The fact is that the decomposition strategies, DWD and LR, are faster in all cases than the global method, full space, F, S, except in the smallest case, C2. F, S, does not converge to its termination criteria after 12 hours for the case of 8 clusters and typically has difficulty resolving issues that consist of 6 clusters or more. F, S, stopped after 12 hours, with just over 7.5% in the duality gap. DWD and LR end all problems with a duality gap of less than 0.5%. DWD shows superior performance to LR in terms of efficiency and robustness. However, LR's performance is superior to F, S, S, demonstrating that as problems grow in complexity, so does the advantage in favor of large-scale methodologies. The results show that parallel methods are significantly faster than monolithic or sequential methods. For large applied problems, there is no valid reason not to use a partition and decomposition technique. In this case, DWD is more effective than LR. The Fourth Industrial Revolution, also known as Industry 4.0, is characterized by the merging of technologies currently being tested or under development, which is disintegrating the boundaries between the physical, digital and biological spheres. This concept was coined by Klaus Schwab in 2016, and this revolution is marked by emerging technological advancements in various fields, including robotics, artificial intelligence, blockchain, nanotechnology, quantum computing, biotechnology, the Internet of Things, IoT, 3D printing, and autonomous vehicles. Industry 4.0 is the current trend of automation and data exchange, especially in the framework of manufacturing technologies and technological development. It mainly includes cyber-physical systems, the Internet of Things and cloud computing. Industry 4.0 creates what are known as smart factories. Within the modular structure of a smart factory, cyber-physical systems control physical processes, create a virtual copy of the physical world, and make decentralized decisions. Through the Internet of Things, cyber-physical systems communicate and cooperate with each other, at the same time as they do with humans in real time and through the Internet. Participants in the value chain offer and use internal and organizational services. A cyber-physical system, CPS, is a mechanism, physical system, controlled or monitored by computer-based algorithms and tightly integrated with the Internet. In cyber-physical systems, the physical and software components are deeply intertwined, where each element operates on different spatial and temporal scales, exhibiting multiple behaviors and interacting with each other in myriad ways that change with context. Examples of CPS include smart grid systems, self-driving car systems, medical monitoring systems, process control systems, manufacturing process monitoring, infrastructure and road monitoring, robotic systems, home automation, and aerial pilot systems. CPS involves a multidisciplinary approach, merging cybernetic theory, mechatronics, and process design and science. Process control is often derived to integrated systems. In embedded systems, there is a tendency to place more emphasis on computational elements and less on the relationship between computational and physical elements. CPS is also like the Internet of Things, IoT, that shares the same basic architecture. However, CPS presents a greater combination and coordination between physical and computational elements. Prior to Industry 4.0 technologies, mathematical programming was a cornerstone of operations research, or it was used for optimization in manufacturing through deterministic models that provided optimal, but static, solutions to planning problems. This optimization vision corresponds to 50 years of system optimization. In contrast, Industry 4.0 integrates real-time data from sources such as sensors and artificial intelligence to create adaptive cyber-physical systems that continuously improve and control the manufacturing process. So stochastic mathematical programming must be a fundamental component of Industry 4.0, which transforms large amounts of data from connected systems into actionable information and automated, optimized decisions. Providing the analytical power to turn raw data from the Internet of Things, IoT, big data, and cyber-physical systems into cost-effective, efficient, and resilient operational strategies. This implies a new vision of optimization, based on autonomous, real-time, distributed and parallel systems, which require a new teaching of mathematical programming. This new methodology involves autonomous, that decides based on what is happening online in real time. Distributed, manufactured based on multiple models that represent parts or agents of the system, and parallel, everything processed in parallel. At the beginning of Industry 4.0, the complete optimization model is run periodically. Currently, all models run the moment you have new information from the IoT measurement system. Each model represents a physical production system, and all models can be synchronized. This methodology is called real-time distributed optimization using asynchronous smart metering systems. The case of smart grids is an application of Industry 4.0. Synchronizing all the smart grids that will exist in a region is practically impossible to do using a monolithic model. Optimization must be done in a parallel and distributed manner. This corresponds to the vision of artificial brains, manufactured by high The artificial brain is the evolution of DSS under the Industry 4.0 revolution, that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. Autonomous real-time routing and distributed optimization. An example of mathematical programming in Industry 4.0. Challenge: modify the traditional vehicle routing process to access to the Industry 4.0 environment. Solution: it implies that all agents, the dispatcher and the vehicles, need to know what information they need to take from smart metering systems, and what information they need to provide to other agents to they make their decisions, to keep the system end-to-end on the path to optimality. This is possible using asynchronous parallel optimization methodologies. Challenge: modify the traditional vehicle routing process to access to the Industry 4.0 environment. Solution: it implies that all agents, the dispatcher and the vehicles, need to know what information they need to take from smart metering systems, and what information they need to provide to other agents to they make their decisions, to keep the system end-to-end on the path to optimality. This is possible using asynchronous parallel optimization methodologies. In the case of freight transport, the traditional process of planning logistics operations in a city could be carried out as follows. At the end of a period, for example, a day, or a shift, a dispatcher plans all routes to fulfill the deliveries, or pickups of the next period. This may involve solving the problem of routing vehicles with time windows on customers, optimizing an objective function according to the company's business rules. Even for small fleets of vehicles, this is a complex mathematical problem, when we consider all the limitations in real systems. The dispatcher generates the route, the sequence of clients, and possibly the route, the sequence of streets, for each vehicle that will be used that period. This schedule is fixed, and it may be considering static travel times for the entire period. That is not true. At the end of the period, the dispatcher updates the database considering the contingencies that occurred during the period, and will start the process again. Given the reality of the process, in which travel times are uncertain, and change dynamically during the period, the programming carried out cannot be optimal. To transit the path of optimality, a dynamic scheduling can use all the power offered by smart metering systems, like Waze, which, in any time, provides rich information for each truck. The best path, or a route close to the best, and a good forecast of the actual travel time. Additionally, it may be possible to obtain historical data on travel times, differentiated by time of day, day of the week of the month, etc. This allows the dispatcher to have up-to-date information to solve a vehicle route issue with time-dependent time and travel time windows, which should produce better results. The dispatch process can be adjusted as follows. At a certain point in the period, the dispatcher plans all routes solving the routing problem with time windows and time-dependent travel time, taking as input data the latest database updated by all smart metering systems, that is, the trucks, Waze, hydroclimatological, and traffic databases. This process would be carried out centrally, to generate a forecast of the route of each vehicle, to be used that day. Each route must be uploaded to MSD, a mobile smart device, such as a Raspberry computer, VDO, iPhone, or iPad, through which data is received from a SM, a smart metering system, such as Waze. During the route, at the end of service on a client, the MSD mobile device asks SM for information about the estimated travel times, and optimal routes to complete the route. With the new information, the MSD can solve a TSP, travel salesman problem, to recalculate the optimal missing route, that is customer service order, and attention times. MSD send that information to the dispatcher, so that, if necessary, it will rearrange the planning of all routes. The approach may be conceived as an artificial brain composed of a network of mathematical models, the VRP dispatcher, TSP problems in trucks, and the mathematical models provided by Waze, and the existing measurement systems. The communication between the algorithms of mathematical problems must be asynchronous, since events occur in the system. Two levels of interconnection can be visualized, with the dispatcher, to coordinate the entire system, and between trucks, to improve truck decisions. To establish the communication protocol between agents, the decoupled view of a routing problem can be considered, which may be solved using Bender's theory, Lagrangian relaxation, column generation, or cross-decomposition. These methodologies already include math communication between algorithms, to improve the solution of the integral optimization problem. Computer power and mathematical programming. The speed of solution is the result of the multiplication of the speed of computer technology multiplied by basic algorithms and by large-scale methodologies. The speed of large-scale optimization methodologies is the result of multiplying the speeds of the basic algorithms by the large-scale algorithm. With Industry 4.0, there is a growth in computational solutions that can interact with each other. All the developments, in mathematics applied to solving real-life problems, converge to parallel processing and the large-scale mathematical programming. Technologically, everything is supported in Industry 4.0, which integrates cloud computing, edge computing and smart metering. This allows us to talk about autonomous real-time distributed optimization. Below are several cases of the impact of parallelism. The image presents an exponential forecast for the growth of quantum processing power. Speed up, effect of multiple processors. Optimization software, parallel computing, benchmarking. Comparative results with different solvers. A graphics processing unit, GPU, is a coprocessor dedicated to graphics processing or floating point operations, to lighten the workload of the central processor in applications such as video games or interactive 3D applications. In this way, while much of the graphics-related stuff is processed in the GPU, the central processing unit, CPU, can be dedicated to other types of calculations, such as artificial intelligence or mechanical calculations in the case of video games. The GPU implements certain graphics operations called primitives optimized for graphics processing. One of the most common primitives for 3D graphics processing is anti-aliasing, which smooths the edges of figures to give them a more realistic look. Additionally, there are primitives for drawing rectangles, triangles, circles, and arcs. GPUs currently have many primitives, looking for greater realism in the effects. GPUs are present in graphics cards. Optimization using GPUs have been made many years ago, all the way to the current maturity. The experiments include several types of algorithms for linear programming. A tensor processing unit, TPU, is an AI accelerator integrated circuit developed by Google specifically for machine learning. Compared to graphics processing units, which as of 2016 are frequently used for the same tasks, these units are implicitly designed for a higher volume of low-precision computation, e.g., from 8 bits of precision. The term has been coined for a specific chip designed for Google's TensorFlow framework. Other AI accelerator designs are appearing at other vendors as well and are aimed at robotics and embedded markets. Google has also used TPUs for Street View word processing and has been able to find all the text in the Street View database in less than 5 days. In photos, an individual TPU can process more than 100 million photos per day. It is also used in RankBrain, used by Google to provide search results. 3 The Tensor Processing Unit was announced in 2016 at Google I/O, although the company stated that the TPU had been used within its data center for more than a year before. The first generation of Google's TPUs was unveiled at the I/O 2016 conference, designed specifically to run trained neural networks. Optimization using tensor computing. Comparative experiments with CPU, GPU, and flow tensor acceleration are presented. 2 types of experiments are carried out. Asynchronous-synchronous parallel, Bender's decomposition optimization. Different types of parallel optimization are analyzed, comparing a monolithic model in plex and synchronous and asynchronous optimization. The advantage of asynchronous coordination is obvious. Cross-decomposition implemented by Ignacio Grossman and his research team. Cross-decomposition CRFLP experiments. The advantage of cross-decomposition is obvious. Cross-decomposition CRFLPT experiments. The advantage of cross-decomposition is greater as the size of the problem increases. In 2004, General Algebraic Modeling Systems Incorporated, GAMS, reported experiments in the speed gained using 200 CPUs in parallel was 60 to 1 times faster, with its corresponding benefit in accuracy, if parallel processing is used to increase the quality of the results. The difference between supercomputing and computing creates a chasm, not a gap. Large-scale mathematical modeling. System decomposition. The problem of optimization of dynamical systems implies high mathematical complexity in aspects related to modeling and computational solution of the mathematical problem, since to be real they involve many variables and constraints, hundreds of thousands and even millions, and in many cases due to their binary mixed and/or nonlinear character. They require computational times, which, despite the new technologies of microelectronics, are still significant. The problem becomes more complicated when it comes to the optimization of systems affected by random processes that demand stochastic optimization models. Conventionally, the concept of large-scale optimization theories is associated with methodologies aimed at the partitioning and decomposition of a problem, and therefore of the system it represents, into multiple subproblems in order to facilitate its solution. It is convenient to define what the concepts of partition and decomposition mean in this document. Partition, the action of dividing a problem into two subproblems by establishing a hierarchical relationship between them. Decomposition, the action of dividing a problem into multiple subproblems with the same level on a hierarchical scale. In general terms, the solution of an optimization problem using large-scale methodologies is based on the partition of the problem into two subproblems that must be solved in coordination. The two most used methodologies are Bender's partition theory, BT Lagrangian relaxation, LR. BT is a primal technique, feasible primal, meets feasibility conditions, also known as outer linearization or decomposition by quantities or resources. In BT, some variables are called coupling, or control, variables, and the remaining variables are dependent, or coordinated. The hierarchical relationship between subproblems implies that at the higher level the coordinating problem acts on the control variables and at the lower level the primary problem is solved on the coordinated variables. This problem is parameterized as a function of the control variables. In response, the primary level returns information to the coordinator focused on the value of the dual variables of the constraints of that level. In its basic form, BT is applicable when subproblems are linear. Decoupled vision of a system, Bender's partition. It involves dividing the problem in two subproblems, the coordinator and the subproblem. The exchange of information implies that the coordinator sends primal variables, and the subproblem dual variables. Decoupled vision of a system, Bender's decomposition. It involves dividing the subproblem into many subproblems, with a single coordinator. Information exchange implies that the coordinator sends primal variables and the subproblem's dual variables. RL is a dual technique, dual feasible, meets optimal conditions, also called interlinearization or decomposition by prices. In RL, the constraints are divided into coupling, or complicating, and the remainder. The structure of the problem is such that if the coupling constraints are ignored, it is possible to conceive of the optimization process as a simpler one, which in many cases can be subject to a process of decomposition into multiple problems of less complexity. Two hierarchically related subproblems are established. At the higher level it acts as a coordinating problem responsible for determining the dual variables of the coupling constraints. At the lower level, a primary problem is solved on the coordinated variables whose objective function is parameterized based on the dual variables under the control of the coordinator. In response, the primary level returns information to the coordinator focused on the value of the solution of the raw variables. Subproblems in RL are not limited to being linear. Decoupled vision of a system, Lagrangian relaxation. Normally LR is broken down into multiple problems. Information exchange implies that the coordinator sends dual variables and the subproblem's primal variables. In both BT and LR, the main problem can be repartitioned or decomposed to generate multi-level solution schemes. The generic process can be defined as: coupling variables were determined, primary in the case of TB, or dual in the case of RL. These variables are what allow the integration of the subproblems of the lower level and will be optimized at the higher level, which is called the coordination level. The matrix blocks of the lower level are determined to establish the subproblems to be solved at this level. The structure of the coordination problem is determined at the top level, which sets values for the coupling variables, which are sent to the lower level to solve parameterized problems based on these values. The information from the lower level, dual variables in the case of TB and primary variables in the case of RL, is incorporated into the coordination problem to generate new values of the coupling variables. The iterative process of solution ends when the information at the lower level does not change the value generated by the coordinator for the coupling variables. Van Roy, 1983, develops the principles for integrating BT with RL and calls them cross-decomposition, CD, which is applied when the coordinator subproblem partition has been performed, and a new partition or decomposition is desired to be performed on the coordinator using a basic theory different from the one previously used. CD is the harmonic coordination of communications between the different subproblems where in each of them information is processed according to the theory used, BT or RL, and information is exchanged according to the connectivity of the hierarchical scheme of the subproblems. The process of splitting and/or decomposing a system begins by studying its matrix structure. The main matrix structures are diagonal angular dual angular, diagonal matrix structure. This structure allows the systems to be decoupled, as they can be optimized independently. The different partitioning and decomposition methodologies seek to divide the problem into two subproblems coordinated in such a way that one or both problems have a diagonal structure, which allows it to be decomposed into several independent subproblems of lower dimensionality. Mathematically, the diagonal structure is written as the formulation. Angular matrix structure. This structure binds the variables together through a set of constraints. It is appropriate for a dual method such as Lagrangian relaxation. Dual angular matrix structure. Suitable structure to perform first a partition and then a diagonal decomposition. Multi-level matrix structure. Matrix of two blocks, the first of the angular type and the second of the dual angular type, suitable for mixing partition and decomposition. Mathematical intelligence underpins the mathematical models that some humans develop to make their decisions. The image presents the list of short introductory lectures on decision-making, artificial intelligence and artificial brains. Since the creation of AI, and the advent of the computer, it can be said that predictive methodologies displaced prescriptive ones, in what was called artificial intelligence. For the convenience of the reader, decision-making artificial intelligence, DMAI, will be presented in comparison to traditional artificial intelligence. The first big difference is that DMAI is based on the study of mathematical intelligence, which focuses on the representation of the physical world through algebraic formulas, or through differential calculus, and solves problems using exact mathematical algorithms, aimed at finding the best decisions. This area of science corresponds to prescriptive analytics. The essence of mathematical intelligence modeling is based on the study of the human brain, based on neuroscientific studies. The result is the production of artificial brains. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus and hippocampus. The hypothalamus is part of the thalamus. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. The neocortex contains millions of neurons that communicate with each other, to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network, that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. Neuroscientific studies associate the network of neurons of the cerebral cortex in layers, and in columns, connected in an organized hierarchical way. In mathematical models, it is common to use a matrix that relates columns with variables, and equations with rows. The normal thing is that these matrices are sparse, structurally similar to that of the human cortex. This section is based on the paper "Why Does the Neocortex Have Layers and Columns? A Theory of Learning the 3D Structure of the World." Neocortical regions are composed of columns and layers that performs robust object learning and recognition. Columns integrate their changing inputs over time to learn complete models of observed objects. Lateral connections across columns allow the network to more rapidly infer objects, based on the partial knowledge of adjacent columns. Because columns integrate input over time and space, the network learns models of complex objects that extend well beyond the receptive field of individual cells. The image presents the hierarchical distribution of neurons in the neocortex, joining brain, neocortical columns, simple neurons and ion channels. This is the starting point of the Hawkins model. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. This is the fundamental representation of the 3D connectivity of neurons in the neocortex. This structure has the same characteristics as those generated when a monolithic model is divided and decomposed into an atomized model, to process it in parallel. This diagram shows a three-level structure. Result of partitioning and decomposition of a system, using a simple methodology of large-scale optimization, like Bender's theory or Lagrangian relaxation. This diagram shows a three-level structure. Result of partitioning and decomposition of a system, using a simple methodology of large-scale optimization, like Bender's theory or Lagrangian relaxation. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. Cross-decomposition makes it possible to establish complex optimization processes, in which multiple large-scale methodologies are used, which allows to adjust the problems to the most convenient methodology for the solution of each subproblem. From the point of view of multi-layer structures, cross-decomposition gives rise to the exchange of information between multiple layers, of different columns, such as the real structure of the human neocortex. Emphasizing that Hai is not an expert in neuroscience, its interpretation of the functioning of the brain is presented. The cerebral cortex stores all the connectivity of the neural networks that make up the brain. The hypothalamus is a region of the brain that plays a crucial role in regulating essential bodily functions, including body temperature, hunger, thirst, sleep, mood, and hormone release. In addition, the hypothalamus helps maintain homeostasis, like the body's internal balance, through its connections with the autonomic nervous system and the endocrine system. It can be said that it is the motor of the brain. It is a vital structure for the harmonious functioning of the body, acting as a central control center for various physiological and behavioral functions. The hypothalamus must coordinate all the processes that the human being carries out. The artificial hypothalamus must connect the multiple mathematical models, algorithms, that are part of the artificial brain, exchanging information between them to obtain a common goal, mathematically an objective function. This activity must be autonomous, permanent, and based on distributed processing. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. This allows us to talk about autonomous real-time distributed optimization. A cognitive robot is an artificial agent, meaning it acts in place of a person, doing things it is designed to do. Cognitive robots are usually machines controlled by a computer program or by electronic circuits. The robot can be a physical mechanical mechanism and/or a virtual software system. An expert system is a computer system that emulates the decision-making ability of a human expert. Expert systems are designed to solve complex problems by reasoning through bodies of knowledge, represented mainly as if-then rules rather than through conventional procedural code. An expert system is a knowledge-based system that uses a knowledge-based architecture where the knowledge base represents facts about the world. The inference engine is an AI-based automated reasoning system that assesses the current state of the knowledge base, applies relevant rules, and then affirms new knowledge on top of the knowledge base, includes skills for explanation, so that it can explain to a user the chain of reasoning used to arrive at a particular conclusion by tracking the activation of the rules that resulted in the statement. It is part of artificial intelligence. The future will be mathematical programming 4.0. Cognitive robots that create cognitive robots that make cognitive robots based on an expert system. Since 1990, HI created Optex, optimization expert system that produces cognitive robots for mathematical programming. Optex is a generative artificial intelligence that works based on an expert system, so it does not require programmers since the expert system solves all doubts about optimization algorithms. Since 1990, Optex, optimization expert system. Optex cognitive robots create Optex cognitive robots that make Optex cognitive robots that. Optimization in Industry 4.0. Normalization and standardization of mathematical programming models. It is necessary to make easy, and sure, the connecting the mathematical models of the organizations. Asynchronous parallel optimization. The solution of a mathematical model in a computer, or in a grid of computers, using the modern's multiprocessing environments. Optimization knowledge expert system, capitalization of the experience acquired in previous optimization process, so that each new optimization process start reading the knowledge stored as cutting planes and or convex hull surfaces that synthesize the optimal behavior of parts of a complex system. Real-time distributed optimization, distribution of the optimization process in many agents that act independently when they received information of the smart metering systems. Union of mathematical programming and artificial intelligence. Two different worlds. Without fear of being wrong, it can be said that as people and organizations travel the path from arithmetic to parallel thinking, an abyss is being generated, which is concretized in the speed with which a society produces knowledge and wealth. Algorithms swarm, the actual state of artificial intelligence using artificial brains. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world.